Hi everyone, I am Aifang. In this study, we investigate the neural activity associated with a spatial context and how that representation transfers or is retrieved later to guide how we efficiently learn associations between reward and context. When we make decisions between two alternatives, we accumulate perceptual information that is dynamic and dynamically influence our choices. When we are faced with choices that are associated with specific contexts, prior fMRI studies suggest that we rely on retrieving from memory the context in which rewards were previously received. Prefrontal cortex plays a critical role in selective retrieval of associations with context from memory to guide behavior, and this memory retrieval process has been associated with highly synchronous activity in memory circuits that involve the temporal lobe and frontal cortex. Studies of spiking activity have also suggested distinct representations are formed by neurons in these regions and are retrieved to guide decisions. It is still unclear, however, how these representations facilitate rule learning that depend on context. So our hypothesis is that context is selectively retrieved to facilitate the learning of associations between reward and context. And we assess whether patterns of neural activity observed in a spatial context are observed again or transferred when a choice is made to facilitate the learning of rewarded choices in that context. To test our hypothesis, we collected response time and choice accuracy from 14 human participants who performed a two-choice decision task. As the participants perform the task, we collect intracranial EEG signals across the brain, and we use the 80 to 120 Hz bandpass filtered signal as a correlate of neural activity, as we have previously shown this to be associated with memory retrieval. We also look at how slower 1 to 50 Hz oscillations are synchronized across brain regions, as this has recently been shown to coordinate information flow in high-frequency power bursts across brain regions. We further look at the association between neural patterns and behavior by modeling decisions as a drift diffusion process in which evidence is accumulated for a choice. To test the influence of context on decisions, we designed a task with a choice rewarded for a pair of object categories. There are two pairs or two rules to learn. Participants learn the rules or rewarded object category in blocks consisting of 120 trials, 60 trials in context 1, followed by 60 trials in context 2. A choice must be made between building a face or cutlery and animal to receive a reward, and the two contexts are beach and forest. Their order is randomized for each block. The pairs of objects are presented in randomized order throughout each context. So for this example pair, we can learn from the feedback the context dependence of the face building rule and the context dependence of the cutlery animal rule. In this example, face is rewarded in both contexts, so we learned that rule 1 is context independent. Cutlery, however, an animal, is rewarded differently in the two contexts, and so we learned that rule 2 is context dependent. For each trial, the participant is first placed in a context for 500 milliseconds. Then the pair of object categories come on. Participants select an object using the left to right arrow keys and are given feedback with a green screen and cha-ching sound for correct choices and a red screen and buzzer sound for incorrect choices. To understand how well the participants learn the rules, we measure the choice accuracy in 10 moving bins within each context shown in the right plot. We found that the performance at the beginning of the new context, C2, is significantly greater than that in C1 when the choice is context independent and dash, but not when the choice is context dependent and solid. And this suggests that the participant recalled the previous context independent rule and more rapidly learned to apply that rule in the new context. It is unclear still whether these behavioral differences are due to neural processes that occur prior to a choice within a trial and facilitates context-independent decisions, or may relate to learning associations from feedback that support subsequent choices. So we explore further the neural activity that could be underlying these behavioral differences. First, to understand the neural mechanisms, we identified representations of context. These representations simply refer to a vector of values for the mean 80 to 120 Hz band power in 100 millisecond windows across all recording electrodes, shown by the schematic on the top right. We trained linear discriminant analysis decoding models to predict context from the neural activity during the presentation of the context, which occurs 500 milliseconds prior to the object cue. This top left plot is one example where we identified the trained model in red that most accurately predicted context. With the trained decoder, we predicted context from the neural response vectors within a 2-second window around choice, and we assume that high prediction accuracy indicates a reactivation of the context representations. We compare the prediction accuracy between context-dependent and context-independent decisions to determine if more reactivation facilitates decisions that depend on context compared to decisions that do not. There was significantly greater reactivation for CD decisions after the choice is made, shown on the bottom left plot. From looking at the model coefficients also, on average across participants, this reactivation involves engagement of the prefrontal cortex, as shown in the brain plot on the right, and altogether the timing and spatial distribution of this neural reactivation suggests that context representations in prefrontal cortex may be retrieved to facilitate the learning of associations between the reward and new context. Given that information about context across episodes are represented across temporal lobe and frontal cortex, we wanted to investigate whether there's coordinated activity associated with the learning of rewards in a new context. We use the hidden Markov model to reduce the dimensionality of the recorded signals into specific neural patterns with distinct spectral and spatial properties, or states, without knowledge of any task timings. Examples of identified states in the raw intracranial EEG signals in the MTL and PFC are shown here. Each brain region has distinct spectral properties for each state, and we computed a denoise HMM regularized time frequency estimate where we used the time courses of the states to recombine the frequency distributions of each state according to the probabilities that the states are on. This estimate reflects an average over all state-specific spectral patterns of the brain region weighted by the probabilities of each state being active. High activity in a frequency band, for example theta for a region like MTL, can suggest that a multi-region spectral pattern that includes high theta activity in MTL and consistently occurs with other spectral patterns in other regions is observed to be active consistently across trials time locked to choice. As before, we look at the change between context 1 and context 2 for the CD and CI decisions. And these plots suggest that MTL and PFC theta activity increases more for decisions that depend on context, and this coincides temporally and spatially with pattern reactivation. Altogether, the findings so far suggest that coordinated cortical activity and reactivation of context representations may underlie a process for forming new associations to learn rules in different contexts. To study the process of accumulating evidence for two-choice decisions and the role of context in reaching those decisions, we model decision-making as a drift diffusion process. And this is formulated in a Bayesian framework as a process of accumulating evidence over time until it crosses either the upper or lower decision boundary. The choice response time, so the combination of reaction time and choice accuracy data, is distributed according to a Wiener distribution that is parameterized by a decision boundary separation, drift rate, and other parameters not discussed here. The drift rate reflects the speed of information processing, where high values mean fast accumulation of evidence. Interestingly, we found no significant difference in the amount of time participants took to reach a decision, regardless of whether it depended on context or not. However, while speed is one aspect of making a decision, accuracy is another important aspect, particularly important here for maximizing rewards. When we model decision-making as a drift diffusion process that depends on both response time and choice accuracy, we find that the speed of accumulating evidence actually differs for CD and CI decisions. Specifically, the drift rate is slower in the new context for CD decisions, shown in the left distribution plot. C2 is when the rule is reversed and conflicts with what had previously been learned in C1 for decisions that depend on context. Now, the role of context representations and coincident theta activity on these differences in the decision process is still unclear, and future work is ongoing to study whether those neural patterns facilitate the context-independent decisions or influence the slower evidence accumulation for the context-dependent decisions. With that, I'd like to acknowledge the lab members across these three groups, the Gold Lab, the Woolwich Lab, and the TAN Lab at the National Institutes of Health and the University of Oxford. Thank you.